everyone, thank you for coming to my talk. My name is Adèle Colas, and today I will present my paper entitled Interaction Fields, Intuitive Sketch-Based Terrain Behavior for Crowd. I am a PhD student at Inria Rennes, and I am in the Wouter team. Today, I will present a method which principal idea to sketch behavior, meaning directly draw how agents behave between one another. The sketch of the behaviors is straightforward, in the manner of what you see is what you get. When I say behavior, what is interesting to us are the global trajectories of virtual humans, also called agents, in the environment, with possible local interactions. This is what crowd simulation is all about. But what is crowd simulation? Crowd simulation can be defined as a computer-generating reproduction of a real crowd motion. There are several applications of crowd simulation. For example, the simulation of evacuation process in case of emergencies. But what is interesting for us now are the applications in entertainment. Crowd simulation is used to model autonomous agent behavior in video games or in movies. It can be used in movies where crowd fills the background of scenes, and in video games to populate a scene and make it seem more lively. A crowd model is a manner of which you will simulate the crowd. Microscopic models see crowd as a whole, like a fluid, and microscopic models simulate crowd as an individual. For the type of behavior we want in entertainment, we use microscopic approaches or agent-based approaches, because what is interesting is the motion of the individuals. In agent-based approaches, there are local interactions. The motion of each agent is influenced by the position of the other moving agents close to him. For example, an agent has to adapt his trajectories to reach his goal while avoiding colliding with other agents. Or an agent could be part of a group and follow its neighbor trajectories. But there could be many other types of local interactions. When we talk about local interaction in crowd simulation, attention has been focused mainly on collision avoidance. We have plenty of solutions for that. For example, Elbing makes an analogy with magnetic repulsion forces, but also Van der Beek with RVO allowed anticipation in avoidance. Finally, Wouter exploited visual variables to better understand how vision can help avoid collisions. All those models handle collision avoidance, but it's only one local interaction among all the possible ones. What is interesting though is that those three methods can be defined as kind of energy costing functions, which will allow to simulate collision avoidance. All velocity in space are assigned an energy. When the agent is close to another, the energy is high, and when it is far, the energy is low. And the goal is to minimize its energy. But then, if it is that easy to model new behavior with those type of cost function, why don't we see much more local interaction than avoidance, group, and following? What is the energy cost function to intercept someone, walk by someone, or cycling around someone? Why is it missing in the literature? Rennes did try to bring a variety of behavior by modeling them as rules, but it is not always easy to combine them, and it's definitely not easy to create new rules. There is still a barrier to creating more and more behavior for the specific need of a simulation. It's not easy to create a behavior of someone hiding from someone, for example, but to us, it seems easy to describe. There is a real difficulty in modeling this behavior in the form of an energy function, which, on the other hand, can be easy to draw. So we would like to resolve this by proposing an intuitive method, and instead of defining the cost function mathematically, we want to draw them. But what about the already existing sketch-based method? Various techniques, like crowd brush from Ulcini, propose a painting-based system to crowd simulation parameter, like populating an environment or creating path for the agent. The pedestrian environment design by McLavin propose an indirect environment level control system where agent behavior can be specified and tuned in real time by adding layers of behaviors. Some techniques use meshes to bend and edit crowds. Kim's approach defines editable cages that enclose animated characters and support space and time manipulation. Finally, all the technique use patches. Crowd patches from Yasin builds from a set of blocks containing pre-computed local crowd simulation that allows to interactively control the environment content by selecting from a set of patches. These techniques are all successful, but they operate on a different scale than the method we propose. The idea of the techniques are rather that it will drive the parameter of the simulation, but they do not allow the addition of new behavior. There is also navigation field. Navigation field from Patil is a method that allows to sketch what agents are doing in the environment. It allows to translate a global planar and to indicate directly where a group of agents should go. It does not allow, though, to sketch new local interaction between agents. So this is what we can conclude for what we just saw. 1. It is not easy to add new behavior in a simulation, and clearly, in crowd simulation, we always see the same local interaction: collision avoidance, following, and grouping. There are methods to make crowd simulation more intuitive, but nothing about local interaction. This is where we sees our contribution. The method interaction field proposes a new sketchpad method for designing local interaction between agents. An intuitive method. There is 3 components for each stage of the framework. First, one would need to sketch the interaction field on a dedicated GUI using the providing tools. Then, the interaction fields are combined and applied in the simulation to acquire the trajectories. For that, we use a software developed by our team, Humans. Humans is a crowd simulation software that replicates various crowd algorithms with cost function. It was enhanced to integrate interaction field and directly takes the sketch as input to propel the agent. At each frame and for each agent, Humans define the neighbors of the agent, specify the vectors given by the field of each neighbors, linearly combine them to extract the new orientation or velocity of the agent. When all of that is done, we can extract the trajectories out of Humans and use the trajectories to animate 3D characters. To animate the agent, we bought a Unity plugin called Motion Matching. So now let's start by defining what is an interaction field. So the main components of my method, interaction fields, are the fields. Interaction fields are basically vector fields that can map a position P to a 2D vector. This vector field can direct the agent movement by defining velocity vector in the case of velocity interaction field. An IF is always defined relatively to a source. Here, the disk in red. What is new here is that the characteristics of the field will depend on the source. The field will translate and rotate according to the source on movement. The source can be an obstacle, an agent, or the environment. An IF can also control the orientation. In that case, the field will map a rotation 2D unit vector to a position P. What we are showing here at the right bottom is the yellow agent circling around the red agent while always looking in the same direction as the red agent, which is the source. This is one local interaction possible with interaction field. But there can be many, many more. So how do we sketch an interaction field? To design an interaction field, users simply hand-sketch them on a dedicated editor. For this, we use control vector, which is the blue curve you see on the screen. Once all the control vectors have been drawn, we get the rest of the field by interpolation. You can correct and edit a field in real time in a trial and error approach. So with a few lines, you can create a new behaviors in terms of minutes. Designing an orientation field is exactly the same. You just draw 4 lines here, and you have the yellow agent circling around the red agent and looking at it. Now that we explained sketching, we want to develop a bit the possible scenarios. It would be interesting for us if the IF could change according to a parameter. For example, a field that moves agent according to the speed of the source. The faster the red agent goes, the further away the yellow agents are expelled. To do this, we need to define three different fields for three key values of the speed of the source. Then we can get the field for each value of the parameter, the speed of the source, by interpolation between those three key fields. Here, the speed of the source is only an example of parameters that we could use. It could be the size of an obstacle or the mindset of the source, for example, if it's calm or nervous. Now we are going to show you scenarios. In this scenario, we have a public in yellow, a VIP that is controlled by the keyboard and is in red, and the source of the parametric field we just drew, and a group of bodyguards in black. The VIP is also source of a field especially for the bodyguards. This field is also a parametric field. When the VIP stops, they surround him, and when he moves, they follow close to him. So, we show that agent can be source of various interaction fields, that they can also be submitted to various interaction fields. And thanks to the simulation software, we can add another layer on top of that, and allow for classical local interaction like collision avoidance to be handled by other algorithms. For example, here the collision avoidance is managed by Orca. An agent of the public also answers to goal reaching. This is how they always go back to their initial position. And then you can see the scenario in 3D. So to animate the agent, we bought a plugin from Unity that applies the motion matching technique. Motion matching is a Ubisoft technology that allows to select, according to a given trajectory, the right animation in the library. It also handles blending between animation. Second scenario. Here we want to do something more elaborate. The field will be centered around the source, as always, but its orientation will depend on an external object. Here you see the field as a source, the red square, but rotates according to the blue agent position. We can control the field not only in relation to a source, but in relation to another element, which will determine here its orientation. So our parameter here is something else. It's the position of the blue agent. To symbolize that, in the editor, on the left, we use a link, the red dot line, We use a link, the red dot line, which means we deport the rotation of the field onto the position of the blue agent. Then, we draw the field as to make the agent inside hide on the opposite side of the obstacle, relatively to the blue agent's position in the GUI. And then, during the simulation, the field which source is the obstacle will rotate around the blue agent position. And by doing so, the hiding spot will always be in the opposite side of the obstacle relatively to the blue agent's position, to the seeker position. This is the beginning of the hide and seek scenario. We have a hider in yellow, a seeker in blue, and a hiding spot in red. So let's complexify a bit the hide and seek scenario. Here we show that we can apply the same field to many sources. The field we just previously sketched was applied to all obstacles in gray and all agents in yellow. You still have a seeker that is in red and a hider in blue. And so you see now that the hider has way more spot to hide. It can hide behind all yellow agents and the whole gray obstacle. The same scenario is also visible in 3D, using motion matching. Finally, the museum example. This scenario takes place in a museum. We aim at simulating agents visiting a room of this museum. So you see here, you have the walls in gray and the painting in blue. So for this, each painting is source of an orientation field and a velocity field to make the agent stop in front of the painting and looking at it. Each agent also has a parametric field that makes the other agents step aside from their field of view when they stop, meaning that they are looking at a painting, and when they move around, a small field only ensuring a collision avoidance. Finally here, the environment is source of velocity field that makes one group of agents circulating clockwise and another group of agents circulating counterclockwise. So now I would like to talk about two aspects of these scenarios. First, the environment. We can use IF to navigate agents through the environment. The interaction field, IF, is then static, like around this pillar. And we find here the same functionality that with navigation field from Pettre². The environment makes agents turn around the pillar, clockwise for the yellow group and counterclockwise for the green group. Second, we can guide the interaction between the agent and certain elements of the scene, like the paintings. By guiding here, I mean making them stop in front of it, and then going back to visiting the rest of the museum. To make them stop, I have to deactivate the environment field that makes them move around and activate the field of the painting. So we need to activate and deactivate the field chronologically. We need temporal orchestration of interaction field, but right now this feature is scripted and it cannot be designed in the GUI interaction field. This is a limitation of interaction field and also a lead for future work. Before we go further and detail the possible future work for interaction field, it seemed important to demonstrate that our method is easily usable for novices. We showed that interaction field could be used to make complex scenarios, but is it easy to use the tool? Indeed, interaction field was conceived so that anyone could easily tackle it and intuitively do whatever scenario desired. To demonstrate this, we asked 22 participants that took part to our user study. They were showed 5 tutorial videos, after which they had to train by sketching scenarios. After the trainings, they were asked to realize 7 tasks of increasing complexity in autonomous manner. The tasks were instruction given with the sentences, some examples that you can see right now on the screen, plus a video showing the desired resulting trajectory. Here, you can see the result with 2 tasks. You can see the instruction at the bottom of the videos of the task, and you can see in green the 22 agents propelled by the 22 interaction field of the participant. And in purple, you can see what was given to the participant as an example of result. After the task, they were asked to answer on a Likert scale about the ease of the task and their satisfaction towards their own results. You see this on the right. We also questioned them about the usability of the tool with a questionnaire based on SUS. The SUS questionnaire was designed by Brock solely to assert the usability of an interface. This questionnaire here received an A- grade, and you can see the result of the Likert scale question on the bottom right now. So we see that the answer about the ease of the task and their satisfaction is always over 5. The participant took maximum 2 hours to realize the overall study and took in average 3.9 minutes to do one task. So overall, all our results were encouraging and supported our tool. I won't detail this more right now, but you can see all of the detail of this user study in the supplementary materials of our paper. To conclude, we presented interaction fields that allows to directly sketch limitless local interaction between agents. Those new interactions were demonstrated with several scenarios, and a user study proved our tool to be intuitive and accessible to many. For future work, we would like to enable field sketching in virtual reality, so that it would be even easier to design new scenarios. It would allow for a designer or a user to directly sketch how they want other agents to behave toward them. It also allows quick trial and error design of the scenarios. We could use the designer motion to directly create the sketch of the interaction field. And finally, it would be easier to assert the realism of the trajectories. We also want to work, as I said earlier, on the time management of interaction field and the combination of interaction field, so that it could be evaluated with time. So I thank you very much for attending to my talk. I will be glad to answer any question you might have.